in the last video, we showed with induction what the Laplace transform of t to the power of n is. It's n factorial over scn plus 1. So while we're very excited about induction, let's use induction again, although we'll only come to it in a few minutes here, to find the Laplace transform of a derivative. And we're going to get to the nth derivative. But for now, let's think about the Laplace transform of the derivative, so of f prime of t. What is this Laplace transform? Well, what we can do is we can write this out as the integral from 0 to infinity of f prime of t times e to the negative st dt. And, okay, sure, our friend integration by parts looks like it might be able to help. In this case, we're actually going to choose u to be this e to the negative st term. U is going to be e to the negative st, and du is therefore going to be negative s e to the negative st dt. Why am I doing that? I'm doing that so that our du, or sorry, dv, is going to be f prime of t dt. Because dv is f prime of t, our v itself is going to be the integral of f prime of t, which is just f of t. And that's why I wanted what we're integrating to be v, is so that we get back to this nice form, just f of t, which we're going to be to work with. Okay, so let's continue this. By integration by parts, it's going to be u times v, so e to the negative st times f of t, evaluated at 0 to infinity. And this is going to be minus the integral from 0 to infinity of v du, f of t times negative s e to the negative st again. It's going to pull out the s, so it's going to be plus s times e to the negative st dt. Okay, that's nice. Saying that phrase a lot. Let's evaluate this. Okay, so we have this bracketed expression. Because, again, our important assumption, s is greater than 0, this exponent will be negative at infinity, and e to the negative infinity definitely is going to pull f of t down to 0, as long as it is tiny bit of jargon. F of t is of exponential order. That means that the s of t will indeed pull it down to 0, and at infinity, this will equal 0 if f is of exponential order, and the majority of functions are. We only care about the ones that are, because the ones that aren't, we can't take their Laplace transform. Yeah, that was a bit of a tangent, sidetrack. Anyway, and now at 0, we plug in 0. We get e to the negative s times 0 is e to the 0 is 1. So minus 1 times f when t equals 0. That's just f of 0. Okay. Plus s times this integral. But this integral, a lot of suspiciously similar things when we're doing induction with the Laplace transform. This integral is suspiciously similar to the Laplace transform of f itself. This is just the Laplace transform of f of t. Okay, what we get now is that this is really a useful result. The Laplace transform of f prime of t, the derivative of any function, equals s times, and again, another way of writing this big f of t, of the Laplace transform of f of t, I'm speaking what I'm going to say before I'm going to say it, is big f of t, big f of s. So another way of writing this Laplace transform is big f of s to save time. So this here, the Laplace transform of a derivative is s times big f of s, the actual Laplace transform of the function, minus 1 times f of 0, so minus f of 0. Okay, let's just take this for a joyride. Let's see if it works. Let's try to find the Laplace transform of cosine. So if you remember, the Laplace transform of the sine of a times t, this equaled a divided by s squared plus a squared. And if you remember, we're running out of time, so I just told you can use the same method of complex exponentials to say the Laplace transform of the cosine of at equals s divided by s squared plus a squared. Now, you're going to prove to you why this is true using our derivative formula. Just to be sure that our derivative formula is correct and it makes sense. Well, the cosine of at is the same as the derivative of the sine of at, but divided by the a that's going to come out. So the sine of at, the derivative of this with respect to t, is a times the cosine of at. So if we say 1 over a times the derivative of the sine of at, this is going to be the cosine of at. Okay, now that we know this, we can plug it into our derivative formula because now we have our expression. That is to say that if we use our derivative formula now, we have that the Laplace transform of the cosine of at equals, and I'm going to pull out the 1 over a because the Laplace transform is linear, equals 1 over a times the Laplace transform of the sine of at prime. So the derivative of the sine of at. Well, if we apply our formula, the Laplace transform of a derivative is s times the Laplace transform of the function itself. So s times the Laplace transform of sine of at is a over s squared plus a squared, minus the function evaluated at 0, minus s of t evaluated at 0. When I said s of at, I meant sine of at. Sine of a times 0 is sine of 0 is 0, minus 0. So what we end up with is the following. This, and then all times 1 over a, from that original 1 over a, right there. And if we just take this out, factor it out, well, not factor, but distribute, what we get is that the Laplace transform of the cosine of a times t, hush for excitement, is a's cancel out, s divided by s squared plus a squared. So it's exactly what we expected. And it's kind of interesting how this s right here, just from the definition of the Laplace transform of derivative, this s just takes the place of this a by the chain rule, and it all just works out, fits really nicely together. All right, so now we know that the Laplace transform of a derivative of a function is indeed s times the Laplace transform of the function minus the function evaluated at 0. Makes sense. Now let's see if we can find a formula for the second derivative. What is the Laplace transform? If you ever tired and want to cheer yourself up, sound like a bad Frenchman and say Laplace transform. What is the second derivative of f of t, Laplace transformified? Well, this formula doesn't have to apply only to functions that aren't derivatives themselves. This is the derivative of any function, and maybe your derivative is a function and it has its own derivative. What I mean to say is that the Laplace transform of the second derivative of a function, wouldn't that be the same thing as the Laplace transform of the first derivative of a function taken the derivative of? Because this is just the same as the second derivative, but now what we can say is, let's use this formula up here. This is going to be s times the Laplace transform of the original function, which is f prime of t, minus your function evaluated at 0, which is f prime of t at 0, which is f prime of 0. Okay, but now we have a formula for the derivative of a function. This is just going to be s times the Laplace transform of a derivative is s times the Laplace transform of the function itself at s, minus the function at 0, and then that all minus f prime of 0. So we get our final formula, which is that the Laplace transform of a second derivative equals s squared times the Laplace transform of the original function, minus s times function evaluated at 0, minus f prime at 0. Let's do just one more example so that it really is solidified why this works and how it's going to work as we do the Laplace transform of the third derivative. Laplace transform of f triple prime of t is the same as the Laplace transform of f double prime of t prime, which is s times the Laplace transform of f double prime of t, minus f double prime evaluated at 0. And then this is just going to be knowing the formula for f double prime. It's going to be s times s squared f of s minus s f of 0 minus f prime of 0, all that times s, minus f double prime of 0. So what we get is that the Laplace transform of a third derivative is the same as s cubed times the Laplace transform of the function itself minus s squared, this s and that s, times the function itself evaluated at 0 minus s times the derivative of the function evaluated at 0 minus the second derivative of the function evaluated at 0. Alright, I think you can see where this is going. What we found is that the Laplace transform of a function raised to the nth derivative is equal to s times the Laplace transform of that function raised to the n minus 1th derivative. And then this is minus f to the n minus 1th derivative evaluated at 0. Now, just like we had when we were doing polynomials, we have this recursive relationship. And we can use it, leverage it, to see what's going on. Because what we see is that anytime we have the Laplace transform of a derivative, like f triple prime of t here, we just have s times what came before it minus that derivative. And what we're going to get then is that this Laplace transform is going to just be, we're going to have n s's on the first Laplace transform term, so s to the n times Laplace transform of your function minus s to the n minus 1 s's, because this term didn't start with an s, it has one fewer s's than this term, minus s to the n minus 1 times your function evaluated at 0, minus s to the n minus 2 times the first derivative of your function evaluated at 0, minus a lot of minuses later, minus s times your nth, well, I should say probably your nth minus 2 derivative evaluated at 0, minus your nth minus 1 derivative evaluated at 0. So this whole huge massive expression is the nth derivative. And it makes sense, given how this recursion was going so far. If we just apply it quickly, we find that the Laplace transform, for example, of the fifth derivative of a function evaluated at t is s to the fifth times the Laplace transform of the function minus s to the fourth times the function evaluated at 0 minus s cubed times the function's derivative evaluated at 0 minus s squared times the function's second derivative evaluated at 0 minus s times the function's third derivative evaluated at 0 minus the function's fourth derivative evaluated at 0. So we see we have these decreasing powers of s, and we have increasing derivatives. And in a way, you see we go from the fourth to the third to the second to the first to the 0th to the, what is this? This Laplace transform of s. In a way, it's almost like the negative one derivative. And negative derivative in the sense that a negative derivative is an integral. Interesting. Anyway, so this is the full formula for the Laplace transform of the nth derivative, and in practice, you're mainly going to be sticking to the Laplace transform of the first and second derivatives in their application to differential equations at least. Alright, with that, I'll see you in the next video.